Dr. Boguszewski is a graduate of Faculty of Biology in Warsaw University, and he received his Ph.D. in Nencki Institute and completed his scientific internship in Yale University in the USA. Paweł, the floor is yours.
Thank you very much for this kind of introduction, and especially thank you for inviting me for this presentation and believing that I will say something interesting. That's good to know that you still believe in me. All right, so the idea behind my today lecture was evolving till the last moment. I just realized that, in fact, I need such a lecture to be told, and instead I just prepare one for you and for myself, and I hope you're gonna enjoy it because it shows a very problematic trend which occurs right now. I mean that we have a huge gap between the technology. From one point, we have very advanced systems that can do almost things that were not possible a couple of years ago. And on the other hand, we have a lot of people, very smart ones, which are still using the methods from 20 or 30 years ago. So my main topic will be how we can analyze the data, especially about the ultrasonic vocalization, but this applies to any kind of behavioral data. And maybe that's gonna be some kind of guideline. So first, we can see increase in interest in ultrasonic vocalizations, both in mice and rats. Just a raw number of papers show us that we are reaching the limit about 70 papers per year, just devoted to or using the ultrasonic vocalization in laboratory rodents. So this is something that should demand the good tools, the good toolbox, and especially it demands some ways of communication and sharing the data. I think those are the weak spots right now. And it looks like it should be very easy. We already got 3 lectures that show us the usefulness of the ultrasonic vocalizations. We mainly focus on rats and mice. Rats got two major classes, alarm calls, which are 22 kilohertz, we cannot hear them, and rat laughter, the noises, the sounds they produce when they are happy or they expect something good to happen. In case of mice, we see much more complex patterns, and this complexity leads to some kind of manual assessment of those calls, and there's a very seminal paper from 2010. He tries to categorize those calls without applying any knowledge. What does it mean? It was just rather recording the sounds of unknown, we cannot say language, but just unknown sounds, and trying to figure out some common features, some commonalities. Maybe they got some biological meaning, maybe not. But that was done, of course, by hand, and that's very tedious work. So recording is relatively easy. You can buy good microphones, good DSP unit, and then you can just record the sound. And later, you need to do something with this stuff. And I'm afraid majority of us working in ultrasounds are doing this manually. And Adam is then sending some nice videos on the Facebook work he's performing at the moment. And also we need a lot of manual cleaning. For example, those are the files from the cooperation with next speaker, Kuba Filipkowski. And as you can see, they were heavily edited just to take out the meaningful parts of the spectrum out of the noise of the cage, out of the noise of the environment. And it's very time consuming. It takes much more time to analyze such a data, to clean it, analyze, categorize, than to record. And that's a bottleneck. Means we cannot speed up some analysis just because we need a very well trained people to perform this kind of analysis. And it's really surprising because if we take a look what's going on the artificial intelligence market, we can see that you can right now buy for really hundreds of zlotys, just tens of dollars, special units that you can hook up, for example, for Raspberry Pi, and that will speed up the image recognition. So you can recognize objects with high accuracy out of the live video. And such devices are based on deep learning. So why shouldn't we use such tools? Especially because they show us that these new toys are able to solve problems that were unsolved for many years. Last year we saw AlphaFold 2, which the computer algorithms rather that was a specially designed computer plus specially designed software that won a special competition to fold proteins. And in fact, this problem of protein folding was for many years one of the biggest problems in biology, as you can see, up to 2016 when AlphaFold came onto the market. The probability of being true was like 40%. With AlphaFold 2, it's close to 90%, means basically we solved that problem. All right, but I said that we have this gap between people that are using very advanced techniques like machine learning and deep learning, and other people, for example, those who still think that data scientists should use Excel. And we can see very interesting social phenomenon, for example, when there was a really huge loss of trust in some very prominent scientists just because they omit couple rows when they put the formula in Excel, and they completely change the data. They analyze this wrong data very accurately, but they were plainly wrong. It also can cost money. For example, I think the biggest loss was $24 million due to Excel copy and paste error. And in case of our field, AstraZeneca in 2011 was thinking that Excel files are good for sharing data. They are not, because they just send not sterile template with personal data of patient. So we need to really focus on tools as well, not only on our scientific part. And just thinking about how we can improve this, the whole process, I thought about something I call the great pipeline of USV analysis. But in fact, this pipeline can apply to any behavioral data. So of course, we have input. Input is something we record during our experiment. In this case, it's just an audio file. And at the beginning, we need something that I'm not going to talk about, means the hardware, the equipment that will pick up the physical sounds from environment and translate it into the digital form. For that, we need microphones, we need special experimental environment, we need to set sampling, the resolution of our signal, so on, so on. But at the end of this process, we got some file. We should agree what kind of file it should be. Usually we use a WAV file, which are plain, not compressed, means huge. But maybe in the future we should move toward the files which are a little bit lossless compressed, means there are, for example, internally zipped like FLAC or other formats. Those files we store, we keep them, we have to mark them, and they are really huge. If you want to record a couple hours of USVs, then you know that it takes even bigger files than the video. And right after, we should apply some pre-processing. Means the signal gonna be very noisy. We should see some noise. We should see some biases noises, which are produced by movement of animals, some environmental noises. All this stuff we need to filter out, and we can do this on the very beginning. That's also tricky, because always when we remove some noise, we remove some signal, and there is always a trade-off, how much noise we want to remove and how much noise we need to leave to still see the signal. And we produce some intermediate files, for example, spectrograms, when we can see the calls. That was exactly what I saw on the previous picture. You can visualize what we want to analyze. And for this, we also need some kind of common format. The process of cleaning, the process of producing spectrum is very time consuming. It's useful to have some immediate output. Next, we need some algorithms to detect our signal. So the cleaning is just blind, but then we have to pick up out of the huge files just parts when we know there is a call, there is some kind of signal produced by animal. And for this, we need algorithms that are able to detect the signal, and also they can actively cancel the noise. After they decide what is good, they can remove what is bad, additionally to the first stage. Later, we need some basic categorization algorithms. Means we can set up some rules. For example, you want calls that are long or short, or that are in a proper frequency. And by those rules that we set, we can say to which bin they belongs. But it's better to use more sophisticated algorithms like machine learning and deep learning, because when we set rules, maybe we are wrong. Maybe we don't know what's really important in such a signal. And sometimes computer can find out some new rules, some new important information in our experiment. And that, I think, should be some system which should be open source, easy to share, but also cloud-based. Means you can keep it on the computer somewhere online, so we have easy access, but also it's easy to share. And that's our direct output from experiment. But later we need to combine the USVs with video, physiology, other metadata, for example, like behavior. And this is needed for data sharing and reproducibility. Means that someone can take your raw data and can check if your right with your analysis if your algorithms are good. And for that, we need to store the raw data, process data, as well as all pipeline. Means someone should be able to just take our input and reproduce the whole path without any trouble. For that, we need API, means special ways of communication with such a system from the computer point of view. All right, this reproducibility is very important because right now we have a crisis. Of course, we cannot repeat all experiments, but many experiments are well done, but not analyzed in a proper way. So there is a discussion in the scientific world that we should do everything what we can to enhance reproducibility. In this case, I said that I think such a system should be a cloud-based, based on remote computers, probably with a web access. And it's really nice to feel your data. You can have a hard drive at your hand, and all you need is to plug it and work with your data. It's sometimes much faster, but if you use a cloud, then you can use also or ability to share with your colleagues. You can work on the same data simultaneously. As well, you can cooperate externally, but also you can use the power of the remote computers. And the good point is that, for example, you don't need to install the software. You don't need to buy it. You just need the access to the remote machine. That's very important because I wrote a lot of piece of software, and usually we have a huge problem to make people use it just because they maybe don't understand how to use it, they don't like it, and maybe the process of installing is too complicated. And I already mentioned about the machine learning. Many people consider machine learning like some magic spell, like Wingardium Leviosa from Harry Potter. That when you use this word, it's like, okay, I don't understand, sounds smart, let's go on. It's really something you can understand in a couple minutes. So the machine learning is just a bunch of algorithms, and their main aim is to solve the problem, not by telling how to solve the problem, not by building algorithm to solve the problem, but just showing examples to computer and force it to learn how to solve the problem. There are several different approaches, like, for example, supervised learning means you provide data that you know what's inside. For example, calls with proper tags. It could be unsupervised learning, where you just throw all the data into the computer and just think that maybe something will come out from your data. You just don't wait for a concrete output. And reinforcement learning, which is like a process, so you just correct the outputs on the way. Here is the deep learning, and the difference is that you just use a different set of algorithms. You can use this machine learning for very different purposes. It's like, for example, for clustering your data, for classification, and for example, for regression, finding parameters of your model. But under the hood, there are just statistical and mathematical methods. It's nothing magical. The biggest magical part is this neural network layer, which you can use for each type of learning, because you build a special network, and the network will learn how to solve a problem, but we have no idea how it works, in fact, internally. It means it builds some representation of the data inside, and each iteration could produce a little bit different model. In fact, it simulates a little bit, it emulates a little bit how the brain works. All right, so to find out whether there are already tools that we can use or some useful approaches that can fit in this pipeline, I try to figure out what's on the market. And there's a lot of different packages, and some are better known, some are not known at all. And I was surprised that many of them, they got this trouble of scientific short-term goals. Means probably someone built a very nice system, for example, based on deep learning, and no one cannot use it, and it just stays in internet and dies. For example, there is a WAAVES system. You can still download it, but it was updated the same year it was published. There is just one publication. So we see that people are trying to build very smart approaches to analyze the data, but those approaches didn't survive. One of the, I'll just explain what the columns that I use in this table. This is the first occurrence of the software or the paper. Last active moment of the software means update or some changes in the software. Platform means on which platform it was built. You can see that majority of people are working in MATLAB. MATLAB is really great tool, but the problem is it's expensive, and you can build a special, for example, Deep Squeak is built that way that you can just download the whole library for free and use it for free, but it's not very user-friendly. Whether it's open source, you can tweet in a code, or even Git. Git is a system to share the the source codes of programs, and many of those projects are on the GitHub. You can just see the progress and all changes for each file in such a system. Whether it's cloud based, working on server, and types of detection. Detection means to detect whether the call is simple classification and deep classification. Those two columns are a little bit fuzzy because sometimes I have no idea how the program works. All right, so first was this WAAVES program, and it shows us this initial pipeline that you have to clean your data, you obtain the WAV file, you clean your data, and remove some artifacts that you know are in a file, and then you try to cure the signal. Means, for example, glue together some fragmented parts of the calls, and then just put them into the bins based on, for example, the length of the bin or the base frequency. So in this case, we have just the first part of my graph without this fancy stuff. And this system was written in MATLAB, and as I said, it was one of the first. There were even discussion in a couple of papers about it, but it's not updated, and probably it's already dead. I mentioned the Deep Squeak, and Deep Squeak was a system this is a system also based on the MATLAB. It's open source. You can read the whole code, and it uses a really advanced neural network, not only to classify the calls, but also to clean the signal. And here is a comparison with previous approaches like Muppet or Ultravox, and it shows that it's very resistant for noise. This is not thanks to the classification of calls, but just for a good algorithm for cleaning the signal. The other is VocalMat, which is quite new last year. It's also MATLAB based, and it works on the spectrogram, means it applies the rules that are applying for a visual analysis, not to the analysis of sound. And this is brand new, and as you can see, the accuracy by the authors, they train a special convoluted neural network, which is right now the most modern approach for neural networks. And they said that their accuracy, sensitivity, and accuracy is highest, much higher than DeepSqueak and other competitors. We can also see the Sonotrack call classification, which is software not open. We cannot see the code, it's just custom made, but it was add a feature to the software that is mainly for recording the USVs. So many people are using this system. And at the very end, USV toolbox, and I'm not going into details, I'm run out of time, but we have Fabrice that is author of this really excellent system, because that's the first system that I want to talk about, which is cloud-based. Means you just drop here your wave and boom, the magic happens, and you see classification and the whole statistic, and you can just download all the stuff, but we still have to wait for a paper and for a scripts that are going to be available after the paper will occur. But I have to say it's, I think, the most promising system right now, which is both for quick analysis, but also for huge, when we will have the scripts in Python for custom pipelines. And Fabrice also is involved in a project, MouseTube. This is a project not to store the data, but just to tag them and for better sharing. And I hope they're gonna join both projects at one point. And at the very end, there is a newcomer this year, Acoustic, which will be a web-based system, but it's paid. So right now it's in a very early stage. All right, so at the very end, just 1 minute or two, we have also a different solution, because right now at Nencki we built a National Center for Advanced Analysis of Biological and Biomedical Imaging. So we are just building 2 computers. One computer will sit in a Mikołajki, and the system will be our micro data center, and we aim for computers that are built especially for artificial intelligence, for TensorFlow imaging. There are new NVIDIA A100 and 100 processor, and we're gonna be in collaboration with a Poznań Supercomputer Center, and maybe we will start our own project on this server. Thank you very much.
Okay, thank you very much, Paweł. There is a question from the audience, so I think one will allow. Kevin, would you like to ask it yourself? I will allow you to talk.
Sure. Can you hear me?
Yes.
Okay. The question is about the classification process after machine learning. So often they mean with machine learning, the supervised machine learning, right? But that implies that there is a training data set. And I often wonder, how should this data set be created? Like how big should it be? Who should be the supervisor of the supervised data set if so many people will use it?
That's a problem because in case of many systems, it works on data of people that are producing the system, and then you just download the model or trying to use the system and you've got a trouble. So in this case, I think it would be useful to have like a single storage for many files, files that are in a common way described. So for example, you have some parts that are manually described by trained observer, many trained observers. And then you can run on this single machine the analysis for many files from different labs. And that way you're gonna just have a really huge set and with a huge variability. So I think we should stop working just on our small computers at home and just move to the large scale data centers.
Thank you.
Okay, thank you.